So if work is the way that energy is transferred into or out of our system, power is the rate at which that energy is transferred into or out of our system. And so we can start by talking about the average power, which says, tell me the rate at which energy was transferred into or out of the system over some discrete chunk in time. So on average, what was the power exerted by some force as it did work? So our definition here is that the average power is equal to how much you change the energy of your system divided by the chunk of time that you're choosing to look at. Well, of course, the way we know to change the energy of our system is to do work on it. And so we can think of the average power as just the work divided by that chunk in time. This lets us think about the units of power. And so the units of power have to have units of work divided by units of time. In SI, we use joules for the units of work, seconds for the units of time. And so one way to talk about the units of power are joules per second. We have a secondary label for this. So the other way that we'll talk about the units of power are watts. So if I happen to have a constant force that's doing work on my system, I know that I can calculate the work done by a constant force is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between those two vectors. So phi here in this expression is defined to be the angle between the force vector and the displacement vector. And so if I plug that into my expression for calculating the average power, what I notice is I can group the displacement term on top with the delta t term on bottom. And so I've got the magnitude of the force times the displacement over time times the cosine of phi. And of course, this displacement over time term, that is the magnitude of the average velocity. So a second way I can calculate the average power is taking the magnitude of the force times the magnitude of the average velocity times the cosine of the angle between those two vectors. So phi here is the angle between the force vector and the average velocity. So instead of talking about the average power, which tells me the rate over some chunk of time, I might be interested in, at a particular instant, how much is energy being transferred into or out of my system? What's that rate? And that's the instantaneous power. And the easiest way to get from the average power to the instantaneous power is basically just to change the particular velocity that you're talking about. So one way to calculate the instantaneous power is basically to say, well, there's a force that's doing some work that I'm interested in figuring out what's the rate at which it's transferring energy into or out of my system. So I'm going to take that force, its magnitude, multiply it by the magnitude of the instantaneous velocity, how fast is my object moving at that instant, times, again, the cosine phi, where phi here is the angle between the force vector and the instantaneous velocity vector. And so this will let me figure out at any instant in time, as long as I know what the magnitude of my force is, how fast my object is going, and as long as I know the angle between those two vectors, then I can calculate the instantaneous power.